So here we have the second part of the discussion of elastic solids. In the previous part of the presentation, I introduced and motivated elastic forces, and then I mainly focused on a concept that can be used to derive elastic forces. We have seen that we start with the definition of some deformation function. From the deformation, also referred to as strain, we compute stress, and from strain and stress we can compute the respective elastic energy. And finally, we take the derivative of the elastic energy with respect to a particle position to compute the elastic force at that particle. I have also highlighted that the elastic forces that we get by following the concept have special highly desired properties. We have seen that elastic forces in an element and also in an entire body sum up to zero, and that they preserve linear and angular momentum of an element and also of the entire body. So elastic forces counteract deformations, but they do not affect the global movement of an elastic object. Now here in the second part of the presentation, I'm going to talk about some additional aspects that are relevant for the simulation of elastic solids. First, we look into damping variance and time step constraints. Then we talk about the contact handling of particles with planes. And finally, I present a visualization technique that is highly popular for elastic solids. But first we look into damping and time steps. Damping is a tool that is often used in the simulation of elastic solids and also generally for all types of particle systems in order to improve the stability of a simulation. If you use an explicit numerical integration scheme to update positions and velocities, then any type of damping typically improves the robustness of a simulation and also allows to use larger time steps. On the other hand, damping is less relevant for implicit formulations that already suffer from artificial damping. There exist different types and different realizations of damping, but the general idea is to model some sort of friction or viscosity. In our context, we typically model damping as a force that is applied to particles, and damping forces are generally proportional to a velocity. This velocity is not necessarily just the velocity of a particle, but it can also be a velocity that characterizes some relative movement among adjacent particles. And damping forces are typically directed in the opposite direction of the considered velocity. So the goal is to reduce a velocity, which means that we would like to reduce the kinetic energy of a particle system. So the simplest and most obvious approach would be to damp the velocities of the individual particles of an elastic solid. We take the velocity vi of particle I and multiply this velocity with some user-defined positive scalar damping parameter gamma. The minus sign accounts for the fact that we would like to accelerate the particle I such that its velocity is being reduced. The second option that I'd like to discuss is the damping of the relative velocity between two adjacent particles. Here we have two particles I and j with velocities vi and vj and positions xi and xj. The force F at particle I due to a relative movement of particle j is directed along the line between xi and xj, and the force magnitude is given by the product of a damping parameter gamma and the relative velocity between the two particles projected onto the line through the particles. This force is actually computed for both particles I and j. It is straightforward to see that the force at particle j is simply the negative of the force at particle I that is shown here. Please also note that the damping force just damps the time rate of change of the distance between the particles I and j. If we have different velocities vi and vj, but the velocity difference does not result in a distance change between the particles from the current to the next time step, then the respective damping force would be zero. A prominent example for such a setting would be particle velocities at I and j that are orthogonal to the connection between the particles. Then the projections of the velocities would give zero, so the damping forces would also be zero. The two discussed damping variants have different properties. If we just damp the particle velocities, then we actually apply external forces that affect the global dynamics of a particle system. So typically we reduce the linear and the angular momentum of the particle system, which means that we slow down the movement of the entire object. We can imagine that this is certainly beneficial for the stability of the simulation, but on the other hand, just slowing down everything is not really elegant. The issue of slowing down the dynamics of the entire object is avoided when we work with damping forces that consider relative velocities. And this is due to the fact that such damping forces are internal forces. They sum up to zero, and the pairwise forces are directed along the connection of two particles, so these forces do not change the linear and the angular momentum of the element formed by the two particles. Nevertheless, such damping forces still reduce the kinetic energy of a particle system by reducing oscillations between adjacent particles and also by reducing noise in the velocity field of an entire object. In a fluid, such forces are referred to as viscosity forces. So in summary, the damping of relative velocities is often preferred to the damping of particle velocities, as the damping of relative velocities does not influence the global dynamics of the objects in a simulation. Nevertheless, the damping of particle velocities is also relevant, for instance, in the context of drag forces. If we, for instance, would like to model the interaction of an object with the surrounding air, then the respective drag forces could be realized by applying forces that damp the velocities of surface particles. Another interesting aspect in the context of damping forces is the usage of explicit versus implicit formulations. On the previous slide, we have seen explicit formulations where we use current positions and velocities, but we could also use implicit formulations where predicted positions and velocities are being used in the computation of damping forces. As always, implicit formulations are more involved to realize, but on the other hand, also more reliable. An example setting where an implicit formulation would be more appropriate is a velocity change of a particle due to some contact handling. If we compute the damping from the velocity prior to the contact handling and the contact handling inverts the particle velocity, then the computed damping force would not damp but add energy instead. Such an issue would be avoided with an implicit formulation where we perform the contact handling first and then the damping force would be computed from the inverted velocity. The next aspect that I'd like to briefly discuss is the handling of particle masses in the simulation of elastic solids. We remember that a deformable solid is subdivided into elements and particles, and that elements and particles represent small volumes with small masses of an object. Now, the discretization is not always uniform, and we typically get particles and elements that represent volumes of different sizes. And here we face the issue that the discretization should not affect the simulation. So large particles or elements should have larger masses than smaller particles or elements. It's trivial, but it should be considered in the initialization of particle systems. When we simulate elastic solids, we often start with a discretization into elements. If we have a 3D object, then we subdivide into tetrahedra. If we have some 2D cloth, then we use triangles. So we start with elements that have a size A as indicated in the illustration. And we have a density ρ that characterizes the material that we want to simulate. Now each element has a volume, a density, and also a mass. And each element is formed by particles, as for instance xi in the illustration. And as we apply our forces to the particles, we need to have a notion of the mass of the particles. This can simply be realized by distributing the volume and the mass of an element to the respective particles. Here in this 2D setting, each element has 3 particles, so 1/3 of the element mass is distributed to each particle. For particle xi in the illustration, this means that we sum up the areas A of all adjacent elements j, multiply with the density ρ of the material, and divide by 3. When we compute the accelerations at the particles, there actually exist slightly different options. First of all, we remember that we compute elastic forces Fji, which means that the force is applied to particle I of element j. Now, when we compute the acceleration at a particle, we can either accumulate the forces and divide by the accumulated mass, or we can accumulate the individual accelerations, where we first divide the force Fji at particle I of element j by 1/3 of the mass of element j. Typically, the first option is implemented as it is easier to realize. The last aspect that I'd like to discuss in this part of the presentation is the setting of the simulation time step. Of course, the time step is mainly governed by the fact that we would like to have a stable simulation, but on the other hand, it would also not be appropriate if elements would move too far within one time step. So if an element is of size d, which is typically a diameter, and if this element moves with velocity v, then time step times velocity should not be larger than the element size. Here the product of time step and velocity is actually the distance that an element travels within one time step, and this distance should not be larger than the element size. If we have elements of different sizes and with varying velocities, then the constraint considers the smallest element and the largest velocity. From the constraint, we can actually deduce a constraint for the time step, which states that the time step h should not be larger than the size of the smallest element divided by the velocity of the fastest element. The proportionality coefficient lambda that relates time step and element size divided by velocity can actually be interpreted as a performance measure. For instance, if we have a time step h that corresponds to lambda equal to 1, then we have the largest possible time step. If on the other hand our time step is limited by the integration scheme, and if the time step corresponds to a smaller value of lambda, for instance equal to 0.1, then we know that there's much potential to improve the stability because we could actually use much larger time steps. Last but not least, I'd like to point out that the specification of a simulation time step is rather meaningless if the time step is not related to the element size. There is no small or large time step without specifying the element size. If the element size is 1 kilometer, then a time step of 1 hour might be small, while a time step of 1 second is certainly huge for an element with a diameter of 1 millimeter. That's it about some smaller aspects related to elastic solids, where I've discussed damping, the handling of particle masses, and the setting of the simulation time step. Now in the following I'm going to discuss an option to handle the contact of particles at walls. Here I'd like to illustrate the problem that we consider. We have an elastic solid that consists of green particles and we have a plane shown in orange. At time t we have a valid state. For instance, we define that a particle is in a valid state if it is above the plane. Now at the next time point t plus h, some particles have invalid states, which we refer to as collisions. We have, for instance, particle I with a collided position xi, and the question is how to correct its position and velocity in a physically plausible way. So in the implementation of a numerical integration scheme, we would predict positions and velocities of all particles, and if particles collide, then the predicted positions and velocities are corrected. Before we discuss the contact handling, I'd like to briefly explain an idea to detect a collision between a particle and a plane. A plane subdivides the 3D space into two half spaces, and for any 3D position we can decide whether the position is in one or the other of the half spaces. And we can define that particles can freely move in one of the half spaces, while the other half space represents some obstacle. Now it turns out that we can compute a signed distance of a 3D position to a plane, which allows us to distinguish the half spaces. If we get a positive distance, we are on one side of the plane. If we get a negative distance, we are in the other half space. In order to compute the signed distance, we start with a plane that is represented by a point xp on the plane and a normalized surface normal n plane. Both quantities are shown in the illustration, and they can be used to characterize the plane that is illustrated by the orange line. From the point and the normal we can implicitly define all points on the plane. If you have a point x for which the scalar product of the surface normal and the vector x minus xp gives 0, then the point is on the plane. So for all points x where the vector x minus xp is orthogonal to the surface normal, we are on the plane. If we have a position x where the respective product is not equal to 0, then the position is not on the plane. And here we have the property that we use to compute the signed distance of point x to the plane. The dot product can not only be used to check whether a point is on the plane, but it also gives the signed distance d of the query point x to the plane. In the illustration, this is indicated for 3 example positions. We see that the scalar product gives a positive distance d for the position x1. For x2, we get a distance of 0, and at position x3, the distance d is negative. The sign of the distance is actually governed by the sign of the cosine of the angle between the two vectors in the scalar product. So an angle smaller than 90 degrees results in a positive value, an angle larger than 90 degrees gives a negative distance. So in the simulation, we have particle positions and some planes, and now we compute the distances of all particles to all planes, and when we get a negative distance, then we handle the contact. In the concept that I'm going to discuss in the following, we basically analyze the relative velocity of a particle to a plane and compute an appropriate physically motivated velocity change or impulse that resolves the detected collision. Now, in order to derive the concept, we first consider the collision of two particles, and after that the scheme is adapted to the particle plane case. So we actually consider the illustrated setting. We have two particles with masses m1 and m2, positions x1 and x2, and velocities v1 and v2. We also consider the direction between x1 and x2, which is represented by the normalized vector n. And now we assume that the volumes of the two particles are in contact, and we would like to compute velocity changes that resolve the contact. In the following, we consider two velocities at the two colliding particles. Lowercase v indicates the velocity prior to contact handling, and uppercase v is the velocity that we get after the handling. And the velocities at the particles can actually be considered in different coordinate systems. Typically, they are represented in some sort of global coordinate system where we perform the simulation. Alternatively, however, it can also be useful to consider the velocities in a rather local coordinate system where one of the main axes is given by the normalized direction n between the particles. To get a coordinate system, we take two additional normalized vectors t and k that are orthogonal to n and also orthogonal among each other. The motivation for the local coordinate system is given by the fact that we have an explicit representation of the normal velocity of the two particles, and we also have the tangential velocity components. So as a first step of the contact handling, we typically transform the velocity prior to the contact handling from xyz space to ntk space. The transformation is just a rotation, and the rows of the transformation matrix are given by the xyz components of the vectors ntk in xyz space. Now the resulting component vn is the velocity in normal direction n, while the other two components describe the particle velocity tangential to the normal direction. And this representation is actually useful for the contact handling. After the contact handling, we perform the inverse transform from ntk to xyz space. Here we have the velocity v after the collision handling in ntk space, and we apply the inverse of the previous transformation to get the corrected velocity in xyz space. So now we work with velocities in ntk space. We know the two particle velocities prior to the contact handling, and we would like to compute the particle velocities after the contact handling. In order to do so, we consider some concepts governing equations and constraints. First of all, we state that the overall momentum of the two particles should be preserved. This can be expressed with these 6 equations for the 3 velocity components at the two particles. On the left-hand side, the components Pn, Pt, and Pk characterize the momentum change at particle 1, and the three equations on the right-hand side state that the momentum change at particle 2 should cancel the momentum change at particle 1. In these equations, the lowercase velocity components are known, the uppercase velocity components and the components of the momentum change, Pn, Pt and Pk, are unknown. So we have 6 equations and 9 unknowns. Now we consider additional equations. We can, for instance, model whether a collision is elastic or inelastic. If a contact is elastic, then the particles bounce away from each other. If the contact is inelastic, then the particles have the same velocity in normal direction after the contact handling. This is expressed with the following equation, where we only consider the normal components of the velocities. And E is the parameter that characterizes whether we have elastic or inelastic contact. This parameter is referred to as restitution coefficient. From the equations, we see that the relative velocity of the two particles in normal direction is inverted for E equal to 1. This means that the particles bounce away from each other. In the other extreme case, for E equal to 0, we see that the difference of the normal velocities of both particles is 0. This means that the normal components of the velocities of both particles are the same. Now we have 7 equations and still 9 unknowns. In the final step, we model friction by establishing relations between the normal and the tangential components of the momentum change. Mu is a parameter, and the equations state that the momentum change in the tangential directions t and k should be proportional to the momentum change in normal direction n. Now finally, we have 9 linear equations in terms of 9 unknowns. The 9 equations form a linear system that can be written in matrix form. The first row, for instance, encodes the relation of the normal components of the velocities to characterize whether we have elastic or inelastic contact. The second and the third row encode the friction equations that state that the momentum change in tangential direction is proportional to the momentum change in normal direction, and so on. So the matrix elements and the vector on the right-hand side are known, while the vector with the momentum changes and the velocities after the contact handling is unknown. Now the solution of the linear system looks like this, and the matrix that we see here is the inverse of the matrix from the previous slide. The matrix is rather large, but it turns out that the size of the system reduces when we do not model a particle-particle contact, but a simplified particle-plane contact. So here at this point we get back to our original problem, and therefore we assume that we have a static plane instead of particle 2. This means that the velocity lowercase v prior to the contact handling is 0. We also assume that the plane or wall has an infinite mass, so the velocity uppercase v would also be 0 after the contact handling. It also turns out that we do not really need to compute the momentum change p. It is just sufficient to compute the velocity uppercase v at particle 1. So actually only 3 rows of the matrix are relevant for us. And as 5 coefficients of the source vector are 0, only 4 columns of the matrix are relevant. So in summary, only a small 3x4 system is actually relevant in our setting. The discussion from the previous slide is summarized here once more. Particle 2 is now considered as a plane with infinite mass and 0 velocity prior and after the contact handling. This means that 5 of the 9 coefficients in the source vector are 0, which also means that the respective columns in the matrix do not contribute to any computation. Now if we would like to compute the velocity of particle 2 after the contact handling, we consider a small part of the matrix from the previous slide and the respective part of the source vector. The last simplification is due to the fact that the plane has infinite mass. This property characterizes the fact that the contact handling only changes the particle velocity, but not the velocity of the wall. Due to the infinite mass of the plane, the mass m2 can be removed from all coefficients. For instance, m2 divided by m1 plus m2 converges to 1 for m2 approaching infinity, and so on. Finally, we end up with three equations that state how to correct the velocity of particle 1 in order to resolve the collision. And in the computations, we just use information from particle 1, and we have two parameters. E governs the contact type and μ governs the friction. In terms of the implementation, the equations are typically slightly changed, and here I'd like to show and motivate the implementation. First, we see the equations from the previous slide and also an illustration. As you can see, the two parameters E and μ can be used to govern the damping of the final velocity in normal and in tangential directions. The damping of the normal component is rather straightforward. We see that for E equal to 1, the normal component of the velocity is just inverted and not damped. Now for smaller values of E, we get some damping. The velocity component is still inverted, but the magnitude is reduced. And for E equal to 0, we have a perfect damping in normal direction. Damping in tangential directions is more complex. We see that the reduction of the tangential components is realized by a term that is subtracted from the original velocity component. And this term depends on the two parameters and also on the original velocity component in normal direction. Now, in practice, it turns out that this term is difficult to handle. We have certain constraints, and it is difficult to guarantee that these constraints are always fulfilled. The constraints are shown here, and they state two facts. The first inequality states that the tangential velocity components should really be damped. So the magnitude of the damped velocity component should definitely be smaller than the magnitude of the original velocity. As μ times E plus 1 times Vtn is not really bounded, the constraint is not automatically fulfilled. The second equation states that the tangential velocity components can be damped, but they should not change their sign. So the tangential velocity components should not be reflected. Now, in order to enforce the constraints, the updates for the tangential components are typically implemented as shown here. If μ is in the range from 0 to 1, then the constraints are fulfilled and μ governs the desired damping. We also see that the proposed computation of the tangential components now follows the form of the update of the normal component. As a last step, we transform the final velocity from NTK space back to XYZ space, as discussed on one of the previous slides. In addition to the velocity, we also have to handle the position of a collided particle. So on the previous slides, we have seen how to correct the velocity in a physically motivated way, but the position of the particle is still in the wrong half space. So how do we handle this issue? One option would be to do nothing. We would just hope that the particle has not moved too far into the wrong half space, and we would also hope that the inverted normal component of the velocity finally resolves the position issue. Another option would be to project the particle onto the plane with the shown equation. We have the distance d to the plane, and we can move the predicted position x star in normal direction n onto the plane. In case of an inelastic contact, this position correction would actually be rather appropriate. For an elastic contact, however, this correction is less accurate. So the position update is generally more challenging and not always perfectly physically motivated. That's it about the contact handling between particles and planes. Now in the last part of the presentation, I briefly present a specific concept that is often used in the visualization of deformable objects. The idea is to use different representations for the simulation and for the visualization. So typically we use a low resolution tetrahedral mesh for the simulation of 3D volumetric objects, and on the other hand we take a high resolution triangular surface mesh that we visualize. It is obvious that both representations do not match each other in an exact way. So the triangular surface is not equal to the surface of the tetrahedral mesh. But both representations are coupled. If the tetrahedral mesh deforms, then the triangulated surface deforms accordingly. Such a concept does not only allow to keep the simulation fast and to use arbitrarily complex representations for the visualization. Instead, it also significantly simplifies the generation of elements for the simulations. As can be seen in the illustration, the tetrahedral elements just roughly approximate the volume that they should represent. And it is generally easier to generate such approximate tetrahedral meshes instead of accurate ones. So here we have a 2D illustration of the two representations that we use for simulation and visualization. We have tetrahedral elements indicated by the blue dotted lines, and we have particles xi that form these tetrahedra. In addition, we have triangles indicated by the orange lines, and the triangles are formed by surface vertices xs. Now the tetrahedra are simulated, the triangles and the surface vertices are transformed accordingly, and finally the triangles are visualized. In order to transform the surface vertices along with the simulated elements, we compute the relative position of a surface vertex with respect to one of the tetrahedral elements. If a surface vertex is inside a tetrahedron, then we just take this tetrahedron, otherwise we would take the tetrahedron that is closest to a surface vertex. Now the relative position of a surface vertex with respect to a tetrahedron can be written like this. x1, x2, x3, x4 are the particle positions of the tetrahedron, and alpha 2, alpha 3, alpha 4 are scalar values. We can actually think of x1 as being the origin of a coordinate system, and the edges x2 minus x1 and so on are basis vectors. Now for each position xs in 3D space, there exists a set of coefficients alpha 2, alpha 3, alpha 4, as long as the tetrahedron is not degenerated. If the volume of the tetrahedron is not equal to 0, then the alpha coefficients represent the relative position of a surface vertex xs inside or near the tetrahedron. The equation can be written in different forms. And instead of writing the equation in terms of the edges of a tetrahedron, the equation can also be written in terms of the particle positions. And here the term 1 minus alpha 2 minus alpha 3 minus alpha 4 is denoted as alpha 1. So a surface vertex xs can be written as alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus alpha 4 x4, where the alpha coefficients indicate the relative position of xs with respect to the particles of the tetrahedron. And we have the constraint that the sum of the alpha coefficients gives 1. Now in this setting, the coefficients alpha 1, alpha 2, alpha 3, alpha 4 are referred to as barycentric coordinates of xs with respect to x1, x2, x3, x4. The computation of the relative position of a vertex inside a tetrahedron is motivated by the fact that we would like to transform the vertex xs along with the tetrahedron. If we have the relative position, then we can reconstruct the position of the vertex xs for arbitrarily translated, rotated, or deformed states of the tetrahedron. The relative position of a vertex inside a tetrahedron can not only be used for visualization purposes, but it can also be used, for instance, for collision detection and handling. If, for instance, a particle collides with a tetrahedron, then the relative position of the particle inside the tetrahedron can be used to derive relevant information, such as the penetration depth. And due to the importance of barycentric coordinates, I'd like to briefly discuss a few properties before we see the usage of the coordinates in our visualization scheme. If all alpha coefficients are in the range between 0 and 1, then the represented vertex xs is inside the respective tetrahedron. If any of the alpha coefficients is 0 or 1, then we are on the surface of the tetrahedron. If, for instance, one coefficient is 1, then the other coefficients are 0, and we are at one of the particle positions. And if any coefficient is negative or larger than 1, the vertex is outside. As already mentioned, the alpha coefficients represent the relative position of a vertex inside a tetrahedron, and these coefficients have to be computed for all surface vertices. So for each vertex, we identify the appropriate tetrahedron and we solve the stated problem. This problem can be written as a linear system where we see that we have three equations with three unknowns alpha 2, alpha 3, alpha 4. The matrix is actually invertible if the tetrahedron is not degenerated, where degenerated means that all vertices would be in the same plane or in the same line or on the same position. If this is not the case, then the alpha coefficients can be computed. And finally, alpha 1 is computed from the constraint that the sum of all coefficients gives 1. Again, for each vertex of the triangulated surface mesh, one set of barycentric coordinates is computed with respect to the closest tetrahedron. So here we have the implementation of the entire scheme. In a preprocessing step, we determine the closest tetrahedron for all surface vertices, and we compute the set of barycentric coordinates for all surface vertices with respect to the corresponding tetrahedron. In the optimal case, the surface mesh would be embedded into the tetrahedral mesh, which means that all surface vertices are inside a tetrahedron. Then, after each simulation step, we reconstruct the positions of the surface vertices from the barycentric coordinates and from the particle positions of the transformed and deformed tetrahedra. The visualization scheme is finally illustrated in the video. We see two instances of the same triangular surface mesh that are attached to two different tetrahedral meshes. The tetrahedral meshes are elastic. They can be transformed and deformed, and the surface meshes move and deform accordingly. You can also see the tetrahedral meshes that are being used for the simulation. As you can see, we can associate a triangular mesh with more or less arbitrary tetrahedral meshes. For accurate simulations, we would use larger tetrahedral meshes that can accurately capture the surface of the simulated volume. But if we are interested in efficiency, then we can also use just a few tetrahedra that only roughly approximate the simulated volume. That's it about the second part of the introduction to the simulation of elastic solids. Thanks for your attention.